Outrun the Sky, a device trusted to save Outrun the Sky, a device trusted to save lives. Each began as a breakthrough and ended up raising questions nobody expected to ask. This isn't just a list of powerful technology, it's a journey through bold ideas, hidden risks, and decisions made under pressure. What happens when innovation moves faster than caution? And how did these machines become legal before the world realized the consequences? Tonight, we're stepping into the stories behind 15 creations that changed the rules, sometimes only after everything went wrong. Ford Pinto, cheap design, deadly consequences. 1970 marked the arrival of the Pinto, a compact car launched by Ford Motor Company at a moment when fuel prices and foreign competition were reshaping the American auto market. The project moved from concept to production in roughly 25 months, unusually fast by industry standards, under pressure from executives, including Lee Iacocca, who pushed strict targets for weight, price, and release timing. Engineers delivered a vehicle that was affordable and easy to manufacture, but its packaging left the fuel tank positioned close to the rear bumper, a detail that would later dominate the safety debates. Crash reports began attracting attention around 1972 to 1973, when investigators noticed that certain rear-end impacts resulted in fuel leaks and fires. Consumer advocates such as Ralph Nader amplified concerns, arguing that relatively small design changes, including protective shields or repositioned components, might have reduced the risk. Public outrage intensified after internal memos surfaced during lawsuits, interpreted by critics as evidence that cost-benefit analysis had influenced safety decisions. Whether every claim reflected the full engineering context or not, the controversy transformed the Pinto into a national symbol of corporate risk management gone wrong. The legal battle reached a peak in 1978 with a criminal case in Indiana connected to a fatal crash. Prosecutors accused Ford of reckless conduct, while the defense argued that the car met federal standards at the time. Ford was ultimately acquitted, but the trial shifted how regulators and manufacturers approached product liability. Agencies such as the National Highway Traffic Safety Administration increased scrutiny on fuel system integrity, and the industry began rethinking how internal safety evaluations were documented and communicated. Long after production ended in 1980, the Pinto remained embedded in engineering ethics discussions. Universities and safety analysts examine it not simply as a flawed car, but as an example of how deadlines, competitive pressure, and financial modeling can shape technical decisions. Its history continues to influence modern crash testing and risk analysis, showing that even small layout choices inside a vehicle can carry consequences far beyond the design studio. De Havilland Comet, the jet age's fatal learning curve. Passengers stepping aboard the Comet in 1952 felt like they were entering the future. Built by de Havilland, the aircraft flew higher and faster than anything civilians had experienced, cutting travel times and transforming expectations of commercial flight almost overnight. Airlines promoted it as a symbol of post-war optimism, and for a brief moment Britain appeared to lead the new jet era while competitors struggled to catch up. That momentum shattered between 1953 to 1954, when several comets broke apart mid-air without clear warning. The accidents baffled investigators because nothing in earlier propeller-driven aviation suggested that a modern airliner could fail so suddenly at cruising altitude. Early theories ranged from pilot error to sabotage, but evidence slowly pointed toward something far more subtle: structural fatigue caused by repeated pressurization cycles. Each flight stretched and compressed the metal skin slightly, and over time microscopic cracks began forming near square cabin windows and riveted joints. A massive investigation, led by the United Kingdom's Royal Aircraft Establishment, took an unprecedented approach. Engineers placed an entire fuselage inside a water tank and simulated thousands of flight cycles, eventually watching the structure fail under controlled conditions. The results changed aviation engineering permanently. Rounded windows replaced square ones, reinforcement methods evolved, and fatigue testing became a central requirement in aircraft certification rather than an afterthought. While redesigned Comet variants returned to service later in the decade, the early grounding created an opportunity for American manufacturers such as Boeing and Douglas Aircraft Company to dominate the rapidly expanding jet market. The aircraft's story became less about commercial success and more about the price of pioneering technology without decades of operational data. Rather than ending as a simple failure, the Comet reshaped how engineers approached pressurized flight. Modern airliners owe much of their structural philosophy to lessons learned during those investigations. Every rounded window frame and every fatigue test performed today traces back to the realization that jet travel introduced stresses no one had fully mapped before the Comet forced the industry to confront them. THERAC 25. Software errors that turned lethal. Hospitals in North America began adopting the THERAC 25 during 1982, a radiation therapy system built by Atomic Energy of Canada Limited that promised precision through software rather than bulky mechanical safeguards. Earlier treatment machines relied on physical interlocks that prevented dangerous configurations, but this new design placed extraordinary trust in code. To many clinicians, the sleek digital interface represented progress. Treatments could be delivered faster, operators could adjust settings quickly, and automation appeared to reduce human error. Few suspected that invisible flaws inside the program could bypass safety layers entirely. Incidents between 1985 to 1987 shattered that confidence. Patients in clinics across the United States and Canada reported sudden burning sensations during routine sessions, followed by severe radiation injuries. Because the machine's screen displayed normal status messages, technicians initially doubted that overdoses were even possible. The gap between what the software reported and what the hardware actually delivered created confusion that slowed investigations. In an era when software engineering standards were still evolving, many professionals struggled to accept that a digital race condition, triggered by rapid keyboard inputs, could silently override protective checks. Detailed analysis later revealed that developers had reused portions of code from earlier systems that relied on mechanical failsafes. Without those hardware protections, minor timing errors allowed lethal beam intensities to activate. Investigators such as Nancy Levison would later examine the case extensively, showing how assumptions about reliability and limited independent testing allowed small programming mistakes to escalate into catastrophic failures. The THERAC 25 became a defining example of how complex human-machine interfaces can conceal risk when feedback systems appear trustworthy. Regulators and hospitals responded by tightening requirements for medical device validation, demanding clearer documentation, redundant safeguards, and rigorous hazard analysis. The machine itself disappeared from clinical use, but its influence spread through software engineering, human factors design, and safety-critical computing research. Instead of being remembered only as a malfunctioning therapy unit, the THERAC 25 stands as a warning that automation changes where danger hides, not whether it exists. When code replaces mechanical protection, invisible logic errors can carry consequences as real as any physical defect. Concorde, supersonic dream with razor-thin safety margins. January 21, 1976, marked the start of regular passenger flights for Concorde, a joint project between Aerospatiale in France and British Aircraft Corporation in the United Kingdom. Designed to cruise at Mach 2, the aircraft turned long transatlantic journeys into short, high-altitude sprints above the weather. Its drooped nose, slender delta wing, and Olympus engines made it instantly recognizable, while premium ticket prices turned every flight into an exclusive experience marketed heavily by Air France and British Airways. Operating Concorde demanded precision that few other airliners required. At supersonic speeds, the aluminum fuselage expanded several centimeters from heat, and engineers had to calculate structural tolerances with extreme accuracy. Sonic boom restrictions limited routes mostly to ocean crossings, while fuel consumption remained extraordinarily high compared with subsonic jets. Even routine procedures, takeoff rotation, climb profile, and descent planning, required careful coordination because the aircraft performed closer to its aerodynamic limits than conventional designs. July 25, 2000, changed public perception overnight. The Air France Flight 4590 crash occurred shortly after departure from Paris Charles de Gaulle Airport, when debris on the runway punctured a tire, sending fragments into a fuel tank. The resulting fire caused loss of thrust and control, leading to the first fatal accident in Concorde's operational history. Investigators introduced modifications, including reinforced fuel tanks and stronger tires, and flights resumed between 2001 to 2003. Yet passenger confidence never fully recovered. The broader downturn in air travel after 2001 further weakened the aircraft's fragile economic model. Unlike many aviation stories that revolve purely around failure, Concorde's legacy sits somewhere between triumph and limitation. It proved that routine supersonic passenger travel was technically achievable decades before modern composite materials existed. At the same time, it revealed how performance pushed to the extreme leaves little tolerance for unexpected variables, whether mechanical, environmental, or financial. When the final flights ended in October 2003, the aircraft left behind more than nostalgia. It left a blueprint showing how ambition can reshape engineering boundaries while quietly exposing the cost of operating at the edge of possibility. Yamaha YZF-R1 Early Models. Speed before rider control. 1998 introduced a machine that felt less like a street bike and more like a barely restrained race prototype. Built by Yamaha Motor Company, the first YZF-R1 arrived during an era when manufacturers competed aggressively for performance headlines. Engineers reorganized the gearbox layout to shorten the engine, allowing a tighter wheelbase and sharper handling geometry. The result was a motorcycle that accelerated violently out of corners and reacted instantly to throttle input. Thrilling for experienced riders, intimidating for everyone else. Unlike modern superbikes packed with electronics, the early R1 depended almost entirely on mechanical feedback and rider skill. There was no traction control watching rear tire slip, no wheelie mitigation adjusting torque delivery, and no lean-sensitive stability system smoothing mistakes. A slight wrist movement could unleash full power from the inline-4 engine, and abrupt throttle transitions sometimes unsettled the chassis. Riders praised its rawness, yet many quickly learned that the bike demanded constant precision, especially on public roads where conditions were unpredictable. The late 1990s to early 2000s performance culture amplified the R1's reputation. Magazine comparisons focused heavily on horsepower numbers and quarter-mile times, pushing manufacturers toward increasingly aggressive tuning. Models like the Honda CBR 900RR and Suzuki GSXR 1000 joined the escalation, creating an unofficial race for supremacy that sometimes prioritized speed over everyday usability. Within this environment, the R1 stood out as a symbol of uncompromised performance, admired in enthusiast circles but occasionally criticized as too extreme for casual riders. By the mid-2000s, the industry began shifting direction. Advances in ride-by-wire technology and electronic control units allowed manufacturers to add layered safety features without sacrificing power. Later generations of the R1 adopted traction control, selectable riding modes, and refined throttle mapping, softening the sharp edges that defined the original versions. That evolution reflected a broader realization: pure performance alone was no longer enough. Manageability mattered just as much. Early YZF-R1 models remain iconic because they captured a transitional moment in motorcycle engineering, the point where mechanical capability surged ahead of digital rider assistance. They didn't just set speed records, they exposed the limits of human reaction time when machines became faster than the safety systems designed to tame them. Titan submersible. Experimental engineering pushed too far. Private deep-sea exploration changed tone around 2018 when OceanGate began promoting Titan as a new kind of crewed submersible, lighter, cheaper, and built around a carbon fiber pressure hull instead of the thick steel spheres used by traditional research vehicles. Founder Stockton Rush framed the project as a necessary disruption, arguing that conventional certification slowed innovation. The design combined titanium end caps with composite materials more common in aerospace than in deep ocean engineering. immediately drawing attention from both investors and critics. Unlike aircraft, which experience outward pressure, a deep-sea vessel must survive constant compression. At depths approaching 3,800 meters near the Titanic wreck, every square inch of the hull endures immense force. Some naval engineers warned between 2019 to 2022 that carbon fiber behaves unpredictably under repeated compression cycles, especially when tiny manufacturing defects or fatigue accumulate over time. Reports later suggested that industry specialists questioned the absence of independent classification from organizations like DNV, a standard step for most commercial submersibles. Supporters viewed Titan as bold experimentation. Skeptics saw an engineering gamble operating without enough redundancy. June 18, 2023 marked the turning point. During a descent to the Titanic site, Titan lost communication with its support ship, the Polar Prince. A multinational search effort dominated global headlines until investigators concluded the submersible had suffered a catastrophic implosion, killing all 5 occupants instantly. The event triggered widespread debate not only about material science, but also about how risk is communicated to paying passengers participating in extreme tourism. Unlike earlier exploration disasters tied to storms or navigation errors, Titan's story focused heavily on design philosophy, how far a company should push unconventional solutions before long-term testing proves reliability. The aftermath pushed regulators, engineers, and investors to re-examine assumptions about innovation at extreme depths. Instead of quietly fading from memory, Titan became a reference point for discussions about verification culture, transparency, and the balance between visionary engineering and proven safety practices. Deep ocean exploration will continue, but the Titan case changed how people interpret the word experimental. It demonstrated that breakthroughs in harsh environments demand not only bold ideas, but also evidence strong enough to withstand forces no human eye can see. Boeing 737 MAX. Automation that pilots couldn't override. Competition inside the commercial aviation market intensified around 2011 when Boeing moved to modernize the long-running 737 platform rather than design an entirely new aircraft. Larger, more fuel-efficient engines were mounted farther forward on the wing to rival Airbus's A320neo family, improving performance but subtly changing how the aircraft behaved during steep climbs. To keep handling similar to older models and avoid expensive simulator retraining for airlines, engineers introduced a software layer called MCAS, the Maneuvering Characteristics Augmentation System, designed to push the nose down automatically if sensors detected an excessive angle of attack. Most passengers never noticed the difference when the 737 MAX entered service in 2017. Yet, inside the cockpit, the automation added a new layer of complexity. MCAS relied primarily on data from a single external sensor, and if that sensor transmitted faulty readings, the system could repeatedly command nose-down trim. Training materials initially described the aircraft as a minor variation of earlier 737 generations, leaving many pilots unaware of how forcefully the automation could intervene during abnormal situations. October 29, 2018, changed the narrative when Lion Air Flight 610 crash occurred shortly after takeoff from Jakarta. Investigators traced a chain of events involving erroneous sensor input and repeated MCAS activation. Less than 5 months later, March 10, 2019, brought another tragedy with Ethiopian Airlines Flight 302 crash, intensifying scrutiny from regulators worldwide. Aviation authorities, including the Federal Aviation Administration, grounded the global MAX fleet between 2019 to 2020, while engineers re-examined software logic, pilot training standards, and certification procedures. The redesign limited MCAS authority, added redundancy through multiple sensor inputs, and required updated simulator training for crews. Airlines gradually returned the aircraft to service, but the crisis left a lasting imprint on how the industry views automation. Instead of treating software as an invisible helper, regulators began demanding clearer documentation of automated behavior and stronger emphasis on human-machine interaction. The 737 MAX story became less about one aircraft and more about a broader transition in aviation design. As cockpits evolve into highly computerized environments, the balance between efficiency and pilot awareness grows more delicate. The events surrounding the MAX demonstrated that automation must support pilots, never outpace their understanding, because even subtle software assumptions can ripple outward into consequences measured on a global scale. Dodge Challenger SRT Demon Street Legal Drag Monster New York Auto Show, April 2017. Dodge pulled the cover off a car that looked less like a commuter vehicle and more like something built for a starting line Christmas tree. The Challenger SRT Demon wasn't designed to be balanced or subtle. It existed to dominate quarter-mile times straight from the factory. Production began for the 2018 model year, and almost every engineering decision revolved around one goal: deliver maximum acceleration within the limits of road legality. Under the hood sat a supercharged 6.2-liter Hemi V8, pushing extreme horsepower figures when fueled with high-octane gas, paired with hardware rarely seen outside professional drag racing. Instead of chasing lap times, the Demon focused on launch physics. Engineers added a factory transbrake, drag-tuned suspension geometry, and wide Nitto drag radials to help transfer weight rearward during hard acceleration. Under ideal conditions, the front wheels could lift briefly off the pavement, a spectacle more associated with dedicated race builds than showroom vehicles. Enthusiasts praised its unapologetic purpose, but critics questioned whether a machine engineered almost exclusively for straight-line speed belonged on public roads filled with unpredictable traffic and inexperienced drivers. Marketing amplified the car's rebellious identity. Buyers received a special crate containing performance components, reinforcing the idea that ownership came with a responsibility to understand the machine's limits. While its explosive launches captured headlines, daily usability was clearly secondary. Fuel economy suffered, cornering agility took a back seat to traction, and the aggressive setup demanded precise throttle control to avoid overwhelming the rear tires. For some drivers, that raw mechanical feel was the entire appeal, a reminder of muscle car culture before electronic safety systems dominated performance design. The Demon arrived during a period when manufacturers competed for viral attention as much as engineering milestones. Rivals pushed horsepower numbers upward, yet few went as far as Dodge in embracing a single-purpose philosophy. Rather than attempting to be an all-around sports car, the Demon celebrated excess, turning factory drag performance into a marketing statement. Even after its limited production run ended, the SRT Demon remained a symbol of how far street-legal engineering could stretch without crossing regulatory lines. It proved that in an era of hybrid powertrains and advanced driver aids, there was still room for machines built around raw torque, spectacle, and a willingness to challenge what practical performance was supposed to mean. Chernobyl, RBMK, reactor. Power without proper safeguards. Reactor number 4 at Chernobyl nuclear power plant was never meant to become a global warning symbol. Built around the Soviet-designed RBMK system, it reflected a philosophy that prioritized output and flexibility. Graphite moderated the reaction, water cooled the core, and fuel assemblies could be replaced while the reactor remained online. For planners in Moscow, the design offered both civilian electricity and strategic potential during the Cold War. What it lacked was the deep margin for error seen in many Western reactors, especially when operated outside strict procedures. April 26, 1986 did not begin with an explosion. It began with a test, a simulation meant to determine whether the turbine's residual spin could generate emergency power during a blackout. Operators reduced output to unstable levels, disabled certain safeguards, and unknowingly placed the reactor into a configuration where physics turned against them. The RBMK's positive void coefficient meant that as steam formed inside the core, reactivity increased rather than decreased. When the AZ-5 shutdown button was pressed, A design flaw in the control rods triggered a sudden surge instead of an immediate stop. Seconds later, 2 explosions tore the reactor apart. The aftermath revealed problems extending beyond engineering diagrams. Initial Soviet reports downplayed the severity, delaying evacuations from nearby Pripyat and confusing international monitoring stations as radiation spread across Europe. Unlike reactors protected by heavy containment domes, the RBMK's structure allowed radioactive debris to escape directly into the atmosphere, amplifying the scale of the disaster. Investigations led by organizations such as International Atomic Energy Agency exposed both design vulnerabilities and systemic communication failures. Surviving IRBMK reactors were modified between 1986 to 1991 with improved control rods, revised operating rules, and stricter oversight. Yet, the deeper legacy of Chernobyl lies in how it changed the conversation around nuclear power. Instead of focusing only on megawatts and efficiency, engineers began emphasizing transparency, human factors, and fail-safe design, reminders that in high-energy systems, small assumptions can carry consequences measured far beyond the control room walls. McDonnell Douglas DC-10, design flaws with catastrophic results. When McDonnell Douglas introduced the DC-10 in 1971, airlines saw a flexible, wide-body jet that could bridge the gap between smaller long-haul aircraft and massive 4-engine giants. Its trijet configuration allowed it to operate from airports that lacked longer runways while still carrying hundreds of passengers across oceans. Early operators, such as American Airlines and United Airlines, quickly integrated it into expanding international routes, and for a brief period the aircraft symbolized efficiency during a rapidly growing era of commercial aviation. Trouble emerged not from a single catastrophic flaw, but from a chain of design assumptions and operational decisions. Engineers chose an outward-opening cargo door to maximize internal volume, yet the complex latch system created a dangerous illusion. The door could appear locked even when internal pins were misaligned. That risk became tragically clear on March 3, 1974, when Turkish Airlines Flight 981 crash occurred near Paris after explosive decompression severed vital control cables. Investigators revealed that warnings about the door mechanism had circulated earlier, raising questions about how safety concerns moved, or failed to move, through regulatory channels. Public confidence suffered another blow on May 25, 1979, during American Airlines Flight 191 crash at Chicago O'Hare. An engine separated from the wing during takeoff, a failure later linked to maintenance procedures that stressed structural attachment points. Although the issue involved airline practices as much as aircraft design, the DC-10's reputation shifted almost overnight. The Federal Aviation Administration grounded the U.S. fleet between 1979 to 1980, while engineers reassessed inspection protocols and structural tolerances. What followed was less dramatic but equally important. Modifications to cargo door systems, updated maintenance guidelines, and refined pilot training gradually restored operational trust. Freight carriers adopted the aircraft heavily, proving that with stricter oversight the platform could perform reliably for decades. Rather than fading into obscurity, the DC-10 evolved into a case study of how complex systems fail, not always because of one fatal defect, but because engineering design, human procedure, and regulatory communication drift out of alignment at the same time. Samsung Galaxy Note 7. Innovation that literally caught fire. August 2016 was supposed to be a milestone moment for Samsung Electronics. The Samsung Galaxy Note 7 arrived as a showcase device. Curved AMOLED display, iris scanning, water resistance, and an S Pen refined for power users who wanted a phone that blurred the line between productivity tool and luxury gadget. Reviewers praised the engineering ambition, especially the decision to fit a large lithium-ion battery into an unusually slim frame. For a few weeks, it looked like Samsung had set the benchmark for flagship smartphones. Then, photos of burned devices began circulating online. Reports between August to September 2016 described overheating units that ignited while charging or even sitting idle. Airlines issued warnings, and safety agencies such as the U.S. Consumer Product Safety Commission launched investigations as incidents spread internationally. Engineers traced the failures to battery cells compressed too tightly inside the chassis, where minor manufacturing defects could trigger internal short circuits. Instead of isolated defects, the issue pointed toward a systemic design tolerance problem. The margin between performance and safety had narrowed too far. Samsung announced a global recall in September 2016, replacing early units with revised models believed to be safe. Confidence briefly recovered, but replacement devices soon showed similar failures. By October 2016, the company made the rare decision to permanently discontinue the Note 7 line, halting production entirely. Billions of dollars were lost, flights banned the device outright, and the incident reshaped public trust in high-capacity mobile batteries. Began reevaluating battery testing, thermal management, and supplier oversight. Samsung itself introduced an 8-point battery safety check involving X-ray inspection, extreme charge testing, and independent verification to prevent future incidents. The Note 7 never returned, yet its impact lingered across the entire smartphone ecosystem. Instead of pushing capacity at any cost, manufacturers shifted toward balancing performance with structural tolerance, proof that even microscopic engineering compromises inside compact electronics can ignite consequences far larger than the device itself. GM EV1. The electric car erased from roads. Traffic in California looked ordinary during 1996, but a small number of drivers were piloting something that felt decades ahead of its time. Built by General Motors, the EV1 wasn't converted from an existing gasoline platform. It was engineered from scratch as a fully electric vehicle shaped by strict aerodynamics and lightweight construction. Its smooth, almost silent acceleration surprised early adopters who leased the car through a tightly controlled program tied to the state's zero-emission mandate. For many, the EV1 felt less like an experiment and more like a glimpse of where everyday transportation was heading. Life with the car came with compromises. Charging infrastructure between 1996 to 2000 remained sparse, forcing drivers to plan routes carefully, and the early lead-acid battery packs limited range compared with traditional vehicles. Later versions upgraded to nickel-metal hydride technology, improving performance but raising production costs. Owners often described the EV1 as strangely futuristic, minimal vibration, instant torque, and a cockpit that emphasized efficiency rather than horsepower. Enthusiasts formed small communities around the vehicle, convinced that electric mobility had finally arrived. Then the narrative shifted. As regulatory pressures evolved and market demand proved uncertain, GM chose to end the program during the early 2000s. Instead of allowing leaseholders to purchase their vehicles, the company reclaimed most units. Images of EV1s being transported to storage yards and eventually dismantled fueled protests from drivers and environmental advocates who believed the technology had been abandoned prematurely. Debates erupted over whether economics, oil industry influence, or infrastructure limitations ultimately drove the decision. The EV1's disappearance didn't erase its influence. Engineers who worked on the project carried lessons into future electric platforms, while policymakers referenced it during discussions about charging networks and battery development. Years later, as modern EVs from companies like Tesla Inc. gained popularity, the EV1 began to look less like a failed experiment and more like an early prototype released before the world was ready. Its short life demonstrated that innovation sometimes arrives ahead of market conditions, not because the technology is impossible, but because timing can shape whether an idea survives long enough to evolve. Belv F-22, Osprey early years. Radical design, deadly trials. Vertical like a helicopter, fast like a turboprop airplane. That was the promise behind the V-22 Osprey when development accelerated under United States Department of Defense during the late Cold War. Built jointly by Bell Helicopter and Boeing, the aircraft used massive rotating nacelles that allowed its prop rotors to tilt forward after takeoff. On paper, it solved a long-standing military problem: Helicopters could land almost anywhere but lacked speed, while fixed-wing transports were fast but required runways. The Osprey aimed to merge both worlds into a single platform. Reality proved harsher than concept art. Test programs between 1991 to 2000 revealed aerodynamic challenges that many pilots had never encountered before. During certain descent profiles, the aircraft risked entering vortex ring state, a condition where disturbed airflow causes rapid loss of lift. Several fatal crashes during training and evaluation drew intense criticism from lawmakers and aviation analysts who questioned whether the tilt-rotor concept introduced more risk than benefit. Each accident forced investigators to look beyond hardware alone, examining how software logic, pilot workload, and unfamiliar flight envelopes interacted under pressure. Rather than abandoning the program, engineers redesigned key systems. Flight control computers were updated to better manage transitions between helicopter mode and airplane mode, and new operational procedures limited descent angles known to trigger dangerous airflow conditions. Training programs expanded to emphasize energy management and situational awareness unique to tilt-rotor flight. These changes gradually transformed the aircraft from a controversial prototype into an operational platform adopted by units such as the United States Marine Corps. The Osprey's early history remains one of the most debated chapters in modern aerospace development. Supporters argue that its speed and range reshaped troop mobility and disaster response capabilities, while critics view the early accident record as evidence of technology pushed too far, too fast. What cannot be ignored is how the program forced engineers to rethink the boundary between helicopter aerodynamics and fixed-wing flight physics. By the mid-2000s, the V-22 had matured into a widely deployed aircraft, yet its difficult beginnings still shape how experimental military aviation is evaluated today. It stands as a reminder that revolutionary designs rarely arrive fully refined. They evolve through hard lessons learned in the air, where innovation meets the unforgiving reality of physics. Takata Airbag System. Safety device turned explosive. Few drivers ever think about the moment an airbag deploys. Yet, for years, the inflators produced by Takata Corporation sat quietly behind steering wheels around the world. Designed to inflate within milliseconds during a crash, the system relied on ammonium nitrate as a propellant, a choice that allowed rapid deployment at lower manufacturing cost. Automakers adopted the technology widely during the early 2000s, integrating Takata components into vehicles from multiple global brands as safety regulations tightened. The danger did not appear immediately. Problems surfaced gradually between 2008 to 2013 as investigators noticed unusual injuries in relatively minor collisions. Instead of cushioning occupants, some inflators ruptured, sending metal fragments through the cabin like shrapnel. Heat, humidity, and long-term aging degraded the chemical propellant, increasing pressure inside the inflator housing. What made the issue especially troubling was its unpredictability. Airbags designed to save lives could become lethal without warning. Regulatory agencies such as the National Highway Traffic Safety Administration began tracing incidents across multiple manufacturers, revealing a defect that spanned millions of vehicles worldwide. Automakers faced the enormous challenge of identifying affected models, sourcing replacement parts, and communicating risk to drivers who might not realize their safety equipment was compromised. As recalls expanded, the scale of the crisis turned it into one of the largest automotive safety campaigns in history, ultimately affecting tens of millions of cars across North America, Asia, and Europe. Investigations exposed deeper systemic issues: pressure on suppliers to reduce costs, inconsistent testing under extreme climate conditions, and delays in escalating early warning signs. The scandal pushed the industry toward stricter traceability standards and more aggressive long-term durability testing for safety-critical components. Manufacturers began reevaluating how they audited third-party suppliers, recognizing that a flaw hidden deep in the supply chain could ripple outward across entire product lines. The Takata case changed the way engineers and regulators think about passive safety systems. Instead of assuming airbags were inherently reliable once certified, Companies now treat inflators as complex chemical devices requiring continuous monitoring throughout their life cycle. It stands as a stark reminder that even protective technology can become hazardous when design margins shrink under the pressure of cost and mass production. Lockheed F-104. Starfighter, the missile with a man inside. Speed defined the vision when Lockheed Corporation began shaping the F-104 under engineer Clarence Kelly Johnson and the Skunk Works team during the mid-1950s. Instead of building a balanced fighter, designers pursued raw interception performance, a thin fuselage, razor-sharp stub wings, and a powerful J-79 engine capable of pushing the aircraft beyond Mach 2. Pilots quickly gave it a nickname that captured both admiration and caution: a missile with a human pilot strapped inside. Everything about the Starfighter reflected Cold War urgency. Minimal wing area reduced drag and boosted climb rate, allowing rapid response against high-altitude threats, yet that same design demanded high landing speeds and precise control inputs. The aircraft excelled in straight-line acceleration, but left little margin for improvisation during low-altitude maneuvering. When NATO allies adopted the jet between 1960 to 1970 for roles far beyond pure interception, reconnaissance, ground attack, and all-weather missions, its narrow performance envelope became more difficult to manage. European operators, particularly the German Air Force, faced a steep learning curve. Early accident rates drew heavy media attention and political scrutiny, with critics arguing that the aircraft's demanding flight characteristics combined with evolving pilot training standards created a dangerous mix. Investigations pointed to multiple factors rather than a single fatal flaw: challenging weather conditions, mission profiles outside the jet's original design intent, and the intense pace of Cold War operations. Over time, upgrades softened some of those risks. Improved avionics, revised training programs, and stricter operational guidelines helped stabilize the aircraft's safety record, and many pilots still praised its unmatched speed and climb performance. The Starfighter went on to set altitude and velocity records that influenced later fighter development, proving how far aerodynamic design could be pushed when performance was prioritized above versatility. The F-104 remains one of aviation's most polarizing machines. To some, it represents engineering bravery, a bold experiment that expanded the boundaries of supersonic flight. To others, it stands as a reminder that extreme specialization can narrow the margin for error when technology meets real-world operations. Either way, its legacy continues to shape conversations about how far designers should push speed before practicality begins to fade behind the horizon.